Здравствуйте все. Меня зовут Juan Carlos Benjamín Luna-Veronico, и я сделаю доклад на тему ЭПР-парадокс, теорема Белла и почему в теории струн говорят, что ER равно EPR. Как вы можете знать, я еще говорю по-русски не очень хорошо, и поэтому я только представляю аннотацию на русском, и после этого я буду говорить по-английски. Извините. Э, Ну, в этом докладе мы рассмотрим ЭПР-парадокс, неравенство Белла и эксперимент Гринбергера, Хорна, Сейлингера, сосредоточить внимание на анализе проблемы локальности и соответствий в определении локальности Белла, а не на обычном подходе отказа от теории скрытых переменных. После этого мы кратко представим АДС КТП или калибровочные, гравитационные или голографическое соответствие, чтобы показать 3 примера, в которых квантовая субстанция отвечает связи двойного голографического пространства-времени и почему из этого следует, что мост Эйнштейна-Росена равно парадокс Эйнштейна-Подолского-Росена. So let me turn now to English, please. And first things first, I don't want to make false expectations in anyone. So uh, you may be thinking as this guy, is this really a true connection? An EPR pair equals an Einstein-Rosen bridge? Of course, it is not. This is just a slogan we use in, well, they use in string theory that relates the entanglement between degrees of freedom of the space-time in certain quantum field theories, how it relates to the connection of the space-time in this holographic correspondence. I will explain everything about that. So this an overview of the talk. I will review very briefly the Stern-Gerlach experiment, the Einstein-Podolsky-Rosen paradox, the Bell's inequalities, the experiment of Greenberger, Horn, Seilinger. All of this focusing more on the locality problem rather on the usual approach, which is the hidden variables theory. I will focus on this, and for this reason, after that, I will present the John Bell's definition for locality. And finally, I will finish the talk talking about this ADS-CFT correspondence, which is a branch of the string theory. And I will present, as I mentioned, 3 examples of this ER equal EPR quote unquote slogan, how it reflects in the theory, and this building up space-time with quantum entanglements. Kind of a surprise that you may find, but let me start, please. So the Stern-Gerlach experiment, as everyone knows, is the first experiment that finds this spin, which is an internal degree of freedom of a particle that manifests itself as an internal angular momentum. And when this particle traverses a region of the space where there is a magnetic field, it acts like a magnetic moment. And contrary to the classical prediction of this magnetic moment taking all a continuous of values, like here, for a beam of spin 1/2 particles, the Stern-Gerlach device in a non-uniform magnetic field splits the beam in exactly 2 parts. The corresponding values are usually called the up spin, which is here in red, and the down spin, which is here in blue. And as it is known, if we measure twice the spin in the same direction, the first state is preserved. I mean, It's like here we split the beam, and after that we measure in the same direction. All the spins will still be up, and all the spins that are initially down will be still in the down state. But if we measure in another direction, which doesn't commute, the original state is like destroyed. This new value measure will have the new state. So spin operators obey the same commutation relationships as orbital angular momentum, and since they do not commute according to the quantum mechanical theory, you cannot have a basis of states that have preassigned values for all of these projections of the spin beforehand. This is the basis of the Einstein-Podolsky-Rosen paradox, which, as you can see, there is always this funny anecdote of Professor Reinhold Bergman, which says that he, despite the color of his right sock, the left one should or must be of a different color. So he's like here wearing a left yellow sock, the other one needs to be from another color, and it is orange in this case. So as I mentioned, I will try to focus on the locality problem. So let me first explain the Gedanken experiment using the Boom's approach, David Boom's approach, which is easier to explain, talking about the spins rather than the original paper. And after that, I will try to say or defend what Einstein tried to emphasize. Didn't well, it didn't happen as the legend says. But well, the idea is that we prepare a source. For example, we need to have an entangled state. One of the possible ones is this singlet state, which has total spin in the projection of zeta 0 and total spin squared equals 0 as well. And what this is telling us is that if we measure, despite how apart all these two devices are in space, if we measure, for example, here a downspin, the other one will necessarily have a upspin. And well, this is known to everyone, so I just want to emphasize that the history says that Albert Einstein was not able to read the final version of this 1935 paper called "Can Quantum Mechanical Description of Reality Be Considered Complete?" And as soon as Boris Podolsky had his version, he sent it to publish, and Albert Einstein was very happy with the result because he said that his main point, which is locality, was not truly emphasized. I will try to explain this. The idea is that Albert Einstein was working full-time on special relativity and after that general relativity. So the locality problem, which means that information or any kind of interaction in physics cannot travel faster than the speed of light in their own frame of reference. I will explain further in a couple of slides, but this is the basic idea. So for this to happen, this quantum, let's call it quantum statistics, are preserved. If we take apart the two Stern-Gerlach devices far and far and far, and this still keep being preserved, we have two options. The first one is that the quantum mechanical theory does not, they call it, is not complete, which is the hidden variables hypothesis that says that, well, of course, what is happening is that they already have a pre-assigned classical value, but you cannot measure it because um, your device is interfering with the value and so on. And well, this is a problem, but in principle, there will be in the future a theory that have these classical pre-assigned values, and we need to take away all this probability description. And the other one that Einstein was very mad with this option is that, well, maybe there is some kind of information that is being transmitted faster than the speed of light, and this could be in contradiction with special relativity, or because some kind of information is traveling faster than the speed of light, so that these two spins, no matter how far they are always into an agreement to have different spins. So this is what they claim. If quantum mechanics is complete, this could imply a violation of locality, or if we believe in the principle of relativistic local causality, we must reject that the quantum mechanical theory is complete, which means we need a hidden variables theory. So, well, Einstein thought that his experiment will not be easy to test in an experimental setup. He cannot imagine how one verify all these well, these two options, or locality or incompleteness. But indeed, John Bell, in his 1966 paper on the problem of hidden variables in quantum mechanics, proposed an experimental setup and a way to test if you want to assign classical values for all the projections of the spin in a entangled state, the same as it is proposed in the EPR paradox, which means that these have indeed classical values pre-assigned for each projection of the spin. The frequencies that they should have will be in a very particular way. This way, it is shown in this image that you can see here on the left. And we have here as well this pair of entangled particles in the same EPR state. And we have two Stern-Gerlach devices, but tilted in an angle with respect to the C projection, theta A, or this one, theta B. And we're going to focus on two pair of angles, to be whatever angles you want. And we're going to focus theta A, theta B, theta B, theta C, theta A, theta C, and different angles. And if we consider the joint probabilities PAB, which means that the particle 1 have a spin up when passing through an Stern-Gerlach device tilted theta A, and particle 2 goes through this Stern-Gerlach device tilted theta B, will have a spin up. Vice versa, the inequality that these frequencies should preserve, it's this. And well, the first experimental setup that tested these Bell's inequalities was made by Aspect and colleagues in 1982 in this paper. And what they found is that there is a strong violation of Bell's inequalities and excellent agreement with quantum mechanical statistics. Making the long story short, there are some situations where no matter how we try to assign probabilities, or in other words, classical values for all the spin projections beforehand, the local hidden variable theory cannot reproduce the quantum mechanical statistics that are observed in real life in the experiment. And there was a even more refined experiment, which is the Greenberger-Zeilinger experiment, which now it has a source that prepares this state, 3 particles, in all of them in the up spin state or all of them in the down spin state. And we are going to measure in these 3 devices different configurations. Could be in the spin in the x direction or in the y direction. And we can literally, the way to decide this can be flipping a coin or whatever you want. And a stochastic way to choose which of the spins we're going to measure. It can be shown that this state, it's an eigenstate of these operators to measure the spin in the x direction for the first particle and a spin in the y direction for the other 2, or spin x in the second one and y for the other 2, or spin x for the third one and y for the other 2, and all of them have eigenvalues +1. I will explain this in detail in the next slide, but using commutation relations between Pauli matrices, it can be proven that this operator, which is measured the spin in the x direction for all 3 particles, can be written as the composition of the product of these 3 operators that I mentioned before with a minus sign. But if we will consider that all spin projection sigma x and sigma y have classical pre-assigned values mx and my, the measured value will be +1 instead of the observed -1, because you know, if you have C numbers for that instead of operators, they don't have these commutation relationships. Let me explain now with a little bit of maths. We have this thing that we want to prove, and we can recall the anti-commutation relationship for the Pauli matrices, which is this one. If we are trying to anti-commute, for n and m are the number of particles, and I and j is the directions in the space. So in our case, sigma x, sigma y for the same particle will change sign when you commute them, and the product of 2 sigma x of sigma x for the same particle or sigma y for the same particle is 1. So in order to from the product of these 3 operators to get sigma x1, sigma x2, sigma x3, we only need to commute this one, well, anti-commute this one, because there's a minus sign that arises here. And after that, we get here a 1. This with this is this with this is a 1. And finally, sigma y2, sigma y2 is another 1. And we have this operator we wanted. And as I mentioned, if we just work with the classical pre-assigned values, we will get the wrong sign because there is no minus sign for interchanging these 2 values. There is a more graphical way to see this that maybe you will like it. This is an argument given by David Mermin in, well, I found it in this book from Tim Maulich, Philosophy of Physics, Quantum Mechanics, and he presents this argument that we have these same values. And we want to, according to the experiment, if we want to measure this sigma x in all of the, there are an odd number of spin-offs here. There should be. And in the remaining configuration, there should be an even number, 0 or 2, of spin-ups. And well, the idea is in the following diagram, we must place spin-ups or spin-downs in a way that along this direction, there should be an odd number of spin-ups, and along this tree direction, there should be an even number of spin-ups. But well, it is easy to prove. It is easy to prove that you cannot achieve this because, well, if we zoom by lines, the number of spin-ups here, you will find that you have odd plus this even. They have odd plus even plus even plus even. The result it's an odd number. And if you add the same thing but by vertices mostly instead, you are counting twice each of the vertices. So this is counted twice, this is counted twice, and so on. So it is 2 times the sum of these values, and this is always an even number. So we get to the contradiction, and this is another way to see why we cannot reassign classical values beforehand, and unless we get a contradiction. So now let me present this Bell's definition of locality. This is maybe this is not known for some people because it is related more with relativity and this kind of thing. So whenever you have any kind of question, you can interrupt me. Well, you always can, especially if something I am not being very clear about that, please let me know as soon as you have a doubt. Well, as I mentioned, first I'm going.
Pardon. So now we are talking about space-time instead of regular particles, common particles like photons, spins, atoms, and so on, right?
Yes. Yes, please. For a moment, please forget discrete systems. Right now, we are going to focus first on this part of space-time. How can I define that a theory respects the definition of locality according to how the signals travel in space-time? And so, yes, that's a good remark. And well, according to Einstein's special relativity theory, the limit speed an object can travel in any frame of reference is the speed of light c. So as you may know, we can construct these light cones, and in this point of space-time, x, t, if we light to the past these two light rays, we can construct this cone, and only things that are inside this cone can reach this event. Well, Bell proposed 4 deterministic theories. When I say deterministic, what does it mean? Is that they have a clear evolution equation, equation of motion, I mean, that if you have all the initial values and the boundary condition, you can predict with full certainty what will be the measured value. So if you have all the information of a slice in this light pass light cone, sorry, this all the information in this sigma slice, whatever physical quantity you want to measure, scalar field like temperature, a vector field like electrical field, magnetic field, tensors, all these quantities should be a function of the information you have in this slice sigma. you can, for example, think, well, maybe in Maxwell theory, you have a particle traveling like this, and well, at this point A, it should radiate and send electromagnetic wave. What happens here? Well, this radiation that happens at this point, indeed, is going to be predicted by the past light cone of this. And as you can see, all the past light cone, the intersections are included in this sigma slice. So if you have the information in this sigma slice, you can predict beforehand that this particle will radiate, and it is all included in this sigma slice. And as well, if you have this other particle traveling in space-time like this, and it radiates here, well, the radiation will pass through this border of this sigma slice, and you can take into account this radiation that will reach this point. And once again, if you have all the information in this sigma slice, you can predict any physical quantity at this point if the theory is a deterministic one and is a local theory. But of course, we don't always have local theories. We have, for example, sorry, we don't always have deterministic theories. We have, for example, quantum mechanical theory, which is not deterministic because, as you may recall, we have two types of evolution in quantum mechanical theory. The first one, the Schrödinger equation, it's deterministic, but when you measure the value of an operator, what happens is this collapse that can be for different values according to some probabilities, and you beforehand cannot know which of these values will take an individual system when you measure it. So this specific collapse evolution is non-deterministic in that sense. So we have a different definition for locality for these non-deterministic theories. And we are going to talk about, instead of physical values, events and probabilities of some events to happen. We are going to say that the non-deterministic theory is local if the probability of an event happening at this point 1 in red here, the conditional probability of this event to happen, knowing all the information in this slice sigma, is the same as if you know also an event happening at this point 2, chi2, and you know these are independent, and you do not have more information knowing what is the event happening here, because the past light cone of this, it is shaded by this slice sigma. Well, I need to emphasize this because since this theory is non-deterministic, if this, despite, for example, here, the point 1 in space-time and point B in space-time are space-like apart, which means that there's no information can travel from B to 1 because it will require to travel faster than the speed of light. If the past light cones intersect and you have something like this, these are not necessarily independent because, of course, for example, looking at this event X, this event is not fully determined because the theory is not deterministic. This event is influenced by this, only influenced, not determined. And knowing what happened in this point of space B, I could have or gain more information of what is happening in X, and this could give me more information of what is happening in 1, but than just having information of this sigma slice. I will give an example of how to apply this in a second in the next slide. If you have any question, please wait after I present this example. An equivalent way of thinking this is imagine that you have this same configuration, knowing the probability of this event chi1 to happen, knowing all the information in this sigma slice, and what is the result of the event chi2 is the same as if another event chi2 prime, an experiment with a different outcome happens here. So it doesn't matter what is the result of this event, the probability is the same. So let me apply this definition to the Newton gravitational theory, which we know that it is not local. And well, imagine that you have three particles, one M, I will call it M blue, M red, and M pink. The M red and M pink particles are in opposite sides of the particle M. So according to the Newton's gravitational theory, the forces are balanced and there is no acceleration, and this particle M, it's in equilibrium. So let me go further on time until we reach this point 1. At this point, I'm going to trace this light cone, and I'm going to give it all the information in this sigma slice. And I will construct this sigma slice so that if I send light rays, they cannot reach any of the M red and M pink particles before at this point of time, at this time, sorry. And we're going to imagine two possible scenarios. One scenario is that this particle stays in the same place, and the other one, I move this particle a little bit closer to the M blue. And well, I'm going to say that chi1 is the event that this particle M blue accelerates, and chi2 is the event that at this point 2, the particle stays in the same place, and chi2 prime, the event in the same point of space-time where I slightly move closer to M blue, this particle. According to Newton's gravitational theory, the probability of this particle to accelerate if the two small masses are in the same place is 0. But if we move this particle a little bit closer, the forces are unbalanced, and in that case, there is an acceleration with probability 1. As we see, the changing the event that is happening here will give us a different probability for this event of found non-zero acceleration here. And that means that according to Bell's definition, Newton gravitational theory is not local. And well, the punchline of all of this, I'm not going to explain in detail, but to wake your curiosity. According to this same Bell definition, quantum mechanics is a non-local theory, which if someone is working in relativity, will make him frightened. That says that quantum mechanics, non-relativistic quantum mechanics, is a non-local theory. And if you are interested in the discussion of this affirmation, I invite you to consult this book of John Bell's Speakable and Unspeakable in Quantum Mechanics, or there's a very good explanation of this as well in the chapter 8 of Travis Norsen, Foundation of Quantum Mechanics. Right. So now I'm going to move to this other part, the final part of the talk, which is the ADS-CFT correspondence. And this theory is way far from quantum optics. So please, any kind of questions you have, let me know. The ADS-CFT correspondence is a branch of the string theory, which in the most broadest sense connects quantum field theories, I mean theories of quantum interacting particles, with dynamical space-time theories, for example, general relativity or string theory. I think ADS-CFT is one of the most productive and when more people is interested nowadays. As you can see, this is the foundational paper of Juan Martín Maldacena, the Larsen limit of superconformal field theories and supergravity. And I checked in a week ago, and it has already almost 20,000 citations. This is the citations per year. And well, this paper is even younger than me, so it's very impressive how people have been paying attention to this topic. Well, Juan Maldacena found these examples of dualities when he was working. I'm not going to get into too much detail, but when he was working in a string theory, in black holes in the string theory type 2B, and the dualities that arise there, and found duality of this correspondence between the supergravity type 2B theory in a low curvature time-dimensional spacetime with a strongly coupled non-gravitational CFT theory, which is the maximally supersymmetric jangles. It is not necessary to understand all of this term, but to understand what I want to say after that, but just in case you are interested. But what is very interesting, it is that also it is not called, as I mentioned, the holographic correspondence, because as you can see here, there is a theory in 10 dimensions that you can translate to a theory in 4 dimensions as a hologram in optics. And there is as well this name called gauge gravity, because this non-gravitational CFT, which is a gauge theory, is translated into a gravitational theory, supergravity in 10 dimensions. I'm going to explain very briefly and without getting into much detail, the basic elements to understand this theory. First, what is ADS? As we always say in string theory, without Escher, all this talk will be very boring. But we have this beautiful painting of Escher called Circle Limit 4. And if you can imagine that all these bats that are being depicted here has all the same intrinsic volume, and well, this is the same size of this, and this tiny one is the same size of this, but due to the space-time, they look smaller here. Then you are imagining, you can have in mind what is ADS. ADS is a solution to the Einstein equation. It's a space with negative constant curvature, which is maximally symmetric, which means that it has all the symmetries as Minkowski, but with negative constant curvature instead of zero curvature. I'm going to mention this strange term is not globally hyperbolic, just to say that contrary to Minkowski, if you send a light ray from the center of ADS, it can reach the spatial infinity and go back to the center in finite time. That is not globally hyperbolic. So you need to specify the conditions at your boundary all the time to have a initial value problem, mean that you can predict all the values with the evolution or the equations of motion correctly. And there are two, the most famous representation for this ADS space, Poincare coordinates and the global coordinates. As you may know, they are related through a diffeomorphism. In general relativity, you can do this diffeomorphism and you are talking about the same object, just a different description. And well, what happens is that with Poincare coordinates, we are just looking at this Poincare patch depicted here in green, which is we unfold it at the boundary. We create this like diamond or rotated square, which is the same Penrose diagram as Minkowski. But if we look the global coordinates, we are representing the whole cylinder we see here, and the boundary of that cylinder is a sphere times time. So these two differences, if we have Minkowski or this sphere in the boundary, it will say which is the dual, the space where the dual theory lives. And just to let me explain this image here. In Poincare coordinates, this is the spacetime, flat spacetime Minkowski, dt dx squared. And this new coordinate C is called the inverse radial coordinate, that it's the inverse of this rho. So at the boundary, C tends to 0, and at the horizon, C tends to infinity. So as you can see here, for different slices of C at a constant Z, as you move further or increase C, this measure of the lengths start to become smaller and smaller as C grows. So that's why we depict that we have this at the boundary, the original space, and when you start increasing C, the lengths will start getting smaller and smaller and smaller. And what is a CFT? A CFT is a conformal field theory, which is just quantum field theory with enhanced symmetry. What do we mean by the enhanced symmetry? As you may know, in quantum field theory, you have the basic symmetries, the Poincare group, which are the rotations in space, the boost in every direction, and the translation in space and time, right? But in a CFT, we also have we can rescale the objects, and we can do this conformal transformation. For example, if you remember your complex variable course, a conformal transformation is just a transformation that preserves the angles, right? So if we have this original space, we do a conformal transformation, all the angles locally are the same. And of course, we have as well another beautiful Escher painting that depicts a conformal transformation. So Escher is always helping us to explain these strange topics. And to have this scale invariance and conformal transformation invariance, we need that the theory don't have an intrinsic parameter like a mass or an energy scale. So if in this kind of, if we will live in a world with a conformal field theory, if you know me in person, I am very small. So in a world with the conformal field theory, I will be the height of my advisor, Professor Kirill, just with founding the correct transformation, right? An example of this is if you recall the Klein-Gordon Lagrangian. This is the kinetic term, and this is the mass term. If you drop out this mass term and remove it, and you remain only with the kinetic term, this is indeed a conformal field transformation, and with any kind of small energy, you can excitate this field and create a particle or something like that. And I'm going to give just 2 examples of the in the real life for conformal field theories to say that they are not just a mathematical invention that does not have anything that corresponds in reality. Quantum chromodynamics, which is the theory that explains the strong force between quarks, gluons, and so on, at very high energies start being weakly uncoupled. This is called the asymptotic freedom effect. And as you may see in this graphic, when you increase the energy of the experiment, the coupling that you find between these objects tends to 0. So the interaction term will start being small and small, and you can only keep the kinetic terms, turning this into a conformal field theory. And also they appear in, I'm not very I don't know too much about that, but in condensed matter systems, when there is critical phenomena, for example, in 2-dimensional Ising model at critical temperature, or 2-dimensional quantum spin chains at this critical point, this can be explained as well with a conformal field theory. I hope that I am not being very boring at this point, but let me just explain it in a very pedagogical way. In a more general view, we, as you see, there are a lot of thousands of examples of quantum mechanical theories very strongly coupled that are equivalent to Einstein gravity theory plus some other fields, quantum fields. This is thought to be that if you have any quantum mechanical theory, it will have a counterpart gravity and string theory, but this is just the conjecture. At the mathematical standpoint, this is just a conjecture. We only have example where it works, but in the most general sense, we would like to have a clear translation between these 2 systems. And well, what we have is just with a strong coupling and with a small string length. Some examples of the holographic correspondence, so you can have an idea of how it works. If I have a CFT theory in the vacuum of Minkowski, which is flat space, it will reflect in a pure ADS space. If I create a excitation of this CFT in Minkowski, it will reflect in a gravitational wave on ADS space. If we have a thermal state in Minkowski, it will reflect in a planar black hole in ADS. A planar black hole is just the difference between a black hole and a planar black hole is the dimensions, right? In our universe, the black holes are spherical, but when we start adding more dimension, you can have this sphere through a linear dimension, which turns into a cylinder instead of a sphere. But if you have this thermal state in a sphere, as I mentioned, working in the global coordinates instead of the Poincare coordinates, what we find is a black hole in ADS, but this black hole more dimensions, but it is a sphere just in more dimensions. You want to find more, I give you this reference. Right now, we are at the point that I can give you the basic idea of this ER EPR, ER equal EPR slogan that I like to say. As I mentioned, it is not that an Einstein-Rosen bridge wormhole it's equal to an EPR pair. What we are just saying is that Juan Malacena and Leonard Susskind, they proposed this slogan because they found that the entanglement in the CFT, it is reflected in the connection of the gravitational theory. What does mean by connection? Well, the first example they find for this is that if we have imagine that we have two copies of this, a CFT living in a sphere, in a thermal state, we have two copies of that, and we are going to create a state connecting the two of them by this specific relation. These two theories are disconnected in space and as well are uncoupled. They do not interact, but we create a state considering both theories. This is a state called the Hartle-Hawking-Israel state, and it has its dual space-time as an eternal ADS Schwarzschild black hole that has a right exterior, a left exterior, and this black hole, well, they share the interior of the black hole. You cannot travel from the left exterior to the right exterior because you need to travel faster than light to achieve that. But Juan Malacena always tells this story that if we can tell once again the story of Romeo and Juliet, that their families put in this left exterior, one of them, and the other one in the right exterior. Well, in this particular case, they can both believe in love and get into the black hole, and they will meet in the future interior. But of course, unfortunately, there is a tragic ending, and they both die at the singularity. But at this point, at least they have some time together in the future interior of the black hole, right? And well, another way to see this figure is that you have a black hole here and another black hole disconnected from this one. And when we have this state in this entangled state, what we are doing is connecting these two throats of the black hole. And well, let me go to the next example. The next example is the Ryu-Takayanagi formula. As I mentioned, we don't have all the ingredients for this theory. It's still an incomplete theory. We cannot find the entanglement of every kind of system, but there's a formula to calculate the entanglement of a region B with its complement A. And the way to achieve that was found by Ryu and Takayanagi. There is this great review to check this. The idea is we're going to find a surface that ends in the same boundary of this region of space-time, but it will need to go through ADS. And we need to verify that this surface has the minimal area, and it does not have a singularity or something strange inside, so that you can push it through B without any problem. A singularity will mean, for example, a black hole. And the holographic entanglement entropy is given by this relationship, very similar to the entropy of a black hole. And you of course need to renormalize the leading divergence because this region B connected to this region A is they share a common boundary, which is this one in red. So of course there is this continuous boundary make the holographic entanglement entropy have a divergence according to this. And we need to remove it, renormalize it. And if we have, for example, this state once again, and we want to calculate the entanglement entropy of this region with respect to the complement, the surface looks like this. For this other region, the surface looks like this, and so on, right? We have like a critical point when you're basically surrounding all the black hole. And if you pass that critical point and you want to check the entanglement entropy of this region compared to this one, the surface is this small one, but as well it has another disconnected part, which is surrounding the black hole because the black hole as well has its own entropy and contributes to the entanglement entropy. Finally, the last example I wanted to share with you is this work done by Mark van Ramsdonk, which is, I think, the most clear example of how can we understand this ER equal EPR relationship. It is called, the papers are called Building Up Space-Time from Entanglement. And the basic idea is that he have a theory living here. He creates an arbitrary partition of the theory between A and A bar and this interface A tilde. When we start reducing the entanglement between these two parts of the spacetime from the CFT theory along this interface, this is reflected in the dual spacetime as the corresponding region for A tilde and the corresponding region for A start to take apart from each other, and the interface between these two regions of the spacetime is being reduced and like pinched. Well, so in the critical case that you remove completely the entanglement between these two parts of the theory, the CFT theory, it is reflected that this space-time breaks into two parts. And in a black hole, for example, like this one, if you start removing the entanglement, what happens is that the two asymptotic regions, the left and this is the asymptotic region from the right, the asymptotic region from the left, they start getting apart and apart. The way we can reduce the entanglement is by descending the temperature or increasing the inverse temperature. And these two asymptotic regions take apart, make the throat even deeper and deeper, so you will never be able to cross from one region to the other. And hopefully you are not asleep at this point. And I just want to close saying that ER EPRs mean that in this particular theory, the entanglement in the conformal field theory reflects itself in the dual theory as the connection of the spacetime. Итак, спасибо за внимание. У вас есть вопросы?
Benjamin, thank you very much for your exciting talk. And can I start with my question?
Yes, of course.
You told us about entanglement.
Yes.
And you mean strong correlations only. When you talk about entanglement, if I understand correctly, you mean strong correlations between two events?
Let me go here. You're saying this a strong coupling, Jimmy? Or
My question, I will continue, maybe you understand my question. I know that there are classical correlations and there are quantum correlations. And if you discuss entanglement in the terms of correlations, how can we understand that you talk about quantum correlations but not classical one?
No, that's good question. Maybe I don't really get the question, but sorry, I am hearing the echo.
I can repeat in Russian.
No, I don't think it will help me. But yes, this what I have talked about is just quantum, well, entanglement in quantum mechanical theory, and I didn't mention classical correlations. I think to be honest, I don't know where I can fit it right here. Maybe we can call correlation this relationship like here, or in these non-deterministic theories. But I'm not sure, to be honest. How can I fit this term of classical correlations?
Well, I
Thank
guess,
you. Maybe another questions?
pardon, but can I add something? I mean, in the case of the classical correlations, of course, you should have a deterministic theory. So so then you are talking about non-deterministic theory. In principle, you well, I mean, it's not the answer to the question of Tatiana Yurievna, but in any case, you should consider a non-deterministic theory, and this is what you have done during the talk. So, in principle, since the theory is non-deterministic, it's not classical one. This is what I mean, and that's why the correlation somehow connected. This should be the quantum correlations instead of classical ones, in my opinion.
Thank you, Kirill. I just comment the last part of Benjamin talk because there he talk about some examples of principles which we cannot include in the non-deterministic part of description. I'm not a specialist here. I'm sorry. It's just my opinion.
This is just both. I am maybe not understanding this classical correlation. I would like to think it of course, since we are like in quantum field theories, every point of the space-time is connected to their neighborhood through this kinetic term. I mean, neighborhood in time and neighborhood in space. Maybe the classical correlations are arising from this thing, but to be honest, I'm not very sure that my answer is what you're having in mind.
Well, Benjamin, I can ask you this question in another way. In principle, if this theory can somehow explain mixed non-separable state. The mixed state, which is can be defined with the density matrix, so on. So I'm not sure that it is the case here, actually.
The mixed state. Well, I think I have read something like that. I'm not very sure. Is the no, I need to check it. Is the no, sorry, I need to check it, and I will I will reach you when I find this paper I have in mind. But they are trying to work in the holographic dual of the density matrix. So maybe they have kind of a sum of light answering this mixed states.
Well, we can discuss it
Yes.
at some point.
Maybe other questions? Benjamin, you give us a lot of ideas for thinking, but not questions, but right now.
Yes, I'm sorry.
Thank you very much. Thank you. It was very interesting.
Не сочетаю.
Дорогие друзья, мы заканчиваем этот сезон, не только этот семинар, но и этот сезон. Спасибо вам за ваше участие и надеюсь до встреч в сентябре.